So as you saw today, we have a whole slew of identities that we're learning. So far we've just done the sum and difference for sine, cosine, and tangent, but today we're going to look at double angle identities for sine, cosine, and tangent, and then we'll look at half angle identities. So those are like all the identities that we're learning this whole chapter. So the idea with double angle identities is like, what happens if we do 2 times an angle? What does that actually look like? Now we looked at some verifications that this could be treated as x plus x, and then we can use like the sum identity, and we know that like the sine of 30 degrees and the sine of 60 degrees are different answers, and the question is, can we just double the answer? Since we're doubling the angle, can we just double the value? So we're going to look at like just an example of that. Like if I know that the sine of 90 is 1, which is true, then is the sine of 2 times 90, is that the same thing as 2 times the sine of 90? Is that true? So let's see, like 2 times the sine of 90, well, that's going to be 2 times 1. But sine of 2 times 90 is really the sine of 180. Well, the sine of 180 is actually 0, so are these things equivalent? Definitely not. So we can't treat it like this. It's not a possibility to say, well, since we're doubling the angle, that's the same thing as doubling the ratio and call it good. Math is not that simple. So we like to complicate things. Let's add some extra layers of complexity to this. And we're introducing this entire stream of double angle identities. Now again, you do not have to memorize any of these identities. Okay, there are different ways to approach all these different problems, or you can see that like cosine is actually, there's 3 different identities that would mean the same thing for the double identity for cosine of 2x, and these can also all be derived from using a Pythagorean identity. We saw this in our verification chapter. Like if I have cosine squared minus sine squared, I can take sine squared out and put in 1 minus cosine squared, and then we get this. Or I can take cosine squared out and put 1 minus sine squared and get this. So we have several different identities or double angle identities that mean the same thing for this by just coming up and making a simple Pythagorean substitution. Same thing over here. Like we actually saw this. You proved it. We proved it yesterday in the verifications that this can be treated as x plus x, and then we can use the sum and difference to actually come up with this double angle identity. Either way, there's lots of different ways that you can use for the cosine and for your sine. There's only like one, and for tangent there's only one. But again, your goal is to be able to apply these identities, not actually memorize them. And to know that this isn't true. We can't just double the angle and call it good, or double the angle and double the value and call it good. So for this first one, we're going to just match it up to the things that we have. So this is 2 times the sine of 15 and cosine 15. Well, that matches up with the double angle identity. So this is now my x value, because that's my argument here. So I am working backwards to represent this as sine of 2 times my x value, which is 15. So this would really be sine of 2 times 15, which is the sine of 30 degrees. Which is something that I can evaluate on my unit circle. The sine of 30 degrees is just 1/2. And again, you can double check this in your calculator. Like if I type in sine 2 times the sine of 15 degrees times cosine of 15, you should get 1/2. So you can double check a lot of this stuff in your calculator and make sure that you're doing things correctly. Same thing here. We're going to match up this identity with one of the ones we're looking at. So this thing matches up with this one. This is my x value. So I'm working backwards and representing it as cosine of 2 times that x value, which is 2 times 22.5. And cosine 2 times 22.5 is 45. So we're really just evaluating the cosine of 45, which is root 2 over 2. So our video is going to be relatively short today because we're only looking at 2, like these are short, quick examples where you're just matching it and working backwards into the double angle. This is an expansion of the double angle identity. But for these ones, we are working forwards and we're coming up with all the identities given that the cosine of theta is 3 over 5. And they tell us that theta is in quadrant 4. So for both of these examples that we do here, we are going to draw in a reference triangle, just like we did for when they gave us like the sine of A equals whatever and the sine of B equals whatever, and we're trying to find the sum difference of cosine of A plus B. Same idea. So we know that theta is in quadrant 4, so here's my reference triangle in quadrant 4. Here's theta. My cosine value is 3 over 5, so adjacent over hypotenuse there, which would mean that this value here is 4, negative 4. So we're finding the sine of 2 theta, and we're going to find the cosine of 2 theta, and then we're going to find the tangent of 2 theta. All three. Now the sine of 2 theta, there's only one identity for that, so if I write out that identity, it's 2 times the sine of theta times the cosine of theta. And again, we're replacing each of these sine of theta and cosine of theta with some sort of evaluation at that angle theta with some ratio. So using my reference triangle, the sine of theta is negative 4 over 5, and we already know it was given to us that the cosine of theta is 3 over 5. So now I can make that substitution that the sine of theta is really negative 4 over 5, and the cosine of theta evaluated is 3 over 5. This is 2 over 1, so I can just multiply everything across. So 2 times negative 4 times 3, well 2 times negative 4 is negative 8, negative 8 times 3 is negative 24, and 5 times 5 times 1 is 25. So the sine of 2 theta is negative 24 over 25. Okay, cosine of 2 theta. Well, we have lots of options. We have lots of different identities that we can choose from. It does not matter which one you choose. I'm going to choose this middle one for really no reason other than I know that cosine is positive and I'm like subtracting here, so I'm just might as well, since I'm given cosine, use that. But again, it really doesn't matter. You can pick whatever identity you want. So we have 2 times cosine of, x would be theta in this case, because that's what the angle that we're using. And whatever we get for cosine of theta, we want to square it. And we know that cosine of theta is really 3 over 5, because they tell us that answer. So this would be 2 times 3 over 5 squared is 9 over 25 minus 1. I double this, so I get 18 over 25 minus 1. And then I subtract 18 minus 25 and minus 25 over 25. We should get negative 17 over 25 for our answer for cosine of 2 theta. And tangent of theta, I can definitely use the identity that's given, so I can find out what tangent is in our problem. The tangent of theta in this case is going to be negative 4 over 3, and then I can replace that in my identity. But since I already found sine and cosine, I might as well just use it. Use those values. If I know that the tangent of 2 theta is really sine of 2 theta over cosine of 2 theta, and I already know that my sine of 2 theta is negative 24 over 25, and I know my cosine of 2 theta is negative 17 over 25, I might as well just plug those values in, and it makes my life easier because when I multiply by the reciprocal, my denominators will always end up canceling out, and we'll end up with negative 24 over negative 17, which is positive 24 over positive 17. Now that's most of our answer. We found the sine of 2 theta, the cosine of 2 theta, and the tangent of 2 theta. But the other part that we needed to do was find the quadrant. To find the quadrant of 2 theta, we do the same way that we found the quadrant of sine, the sum of difference for sine and cosine. We look at the sines of our sine, cosine, and tangent. Now we know theta is actually in quadrant 4, but what happens if we double that angle? It's not necessarily going to be in quadrant 4 anymore. It's going to move somewhere around our circle. So like, let's pick an angle like 300. That's in quadrant 4. If I double it, I'm dealing with the angle of 600, and that's not in quadrant 4 anymore if I find the coterminal angle. So you have to be careful, like it's not going to stay in the same place. But we can do that by analyzing the signs of sine and cosine and tangent. This sign here is negative, this sign here is negative, this one's positive. You really only need to analyze sine and cosine to get your answer. So if I know that my sine is negative and my cosine is negative, that means I'm sitting in quadrant 3. Okay? So that's a forward example. Basically, you're just directly applying all of the the double angle identities. Given that you have some ratio, we always want to draw a reference triangle for these ones. Same thing for the sum and difference when you're given like sine of A and cosine of B, and then you're trying to find the sine of sine of A plus B and the cosine of A plus B. We always are going to draw a reference triangle for it. Okay, this one's a little bit different. This time we're given a double angle and we have to work backwards to try to figure out sine, cosine, and tangent. Now, there are like some easy ways to do this problem, and then there are like some harder ways to do this problem. I'm going to stick with, like, I guess we can talk about both, but I'll go over like the easier way too once we get to a place that we can actually use. So we have the cosine of 2 theta is 4 over 5. So we're starting on this side, and we have to like work backwards to get to this. Now, for your identities, there are 3 different identities that you can choose from. So we can either do cosine squared minus sine squared. You can do 2 cosine squared minus 1, or 1 minus 2 sine squared. Now for all of these that we are given, oops, sorry, I didn't mean to square that. For all these that are given, we're given cosine of 2 theta. Like that's the value that we're given is 4 over 5. So that would be like my replacement of all these things. Now if I start to replace that and look at my identities, and I won't write out this one because it's essentially the same. Is there any way that I can solve for cosine or sine given this problem? Not really, right? Like these are 2 independent things. There's no way that I can actually solve for that. But if I work on this one, there is a way that I can isolate cosine. So I'm not going to use this one, even though it's true. Like I'm not going to use this identity to choose from. You kind of have to pick your battles and figure out like which one is the most appropriate in the situation. I'm going to start with this one. So if I try to isolate cosine, I'm going to add 1 to both sides. So I'm adding 5 over 5, so I get 9 over 5 equals 2 cosine squared of theta. And I'm still isolating cosine, so I'm going to divide by 2, which means I'm multiplying by the reciprocal. So I get 9 over 10 is equal to cosine. And then to get cosine by itself, I need to take the square root. So take the square root of the top, I get 3. Take the square root of the bottom, I get 10. I rationalize. We get 3 root 10 over 10. There's one thing that we forgot when we were taking the square root. We haven't done it in a really long time, but when we take the square root of both sides, we have to remember to include a plus or minus. So altogether at the end, we're deciding, all right, well, is the cosine of theta the positive 3 root 10 over 10 or the negative root 3 over 10? And there's no real way to know that unless it's given to you. So they tell you, actually, that theta is in quadrant 2. That not really necessarily talking about 2 theta, but theta is in quadrant 2, which means that this thing is negative. We need to take the negative version. Cosine is actually negative 3 root 10 over 10. Now from here, since we're coming up with sine and tangent, what I would do from this case is to now draw a reference triangle with only theta. So not really talking about it with 2 theta. Like you might be tempted to draw a reference triangle here, but this is talking about 2 theta, and you don't want 2 thetas over here. Like you want theta only. So when you draw your reference triangle, like this one was a little bit different because we are using theta. Like we wanted 2 theta, but we were like using thetas to come up with the sine of theta and cosine theta. This time we want like sine of theta and cosine theta and tangent theta, but we're given sine of 2 theta. So that reference triangle won't give us anything because we'll just be getting our ratios of sine of 2 theta and tangent of 2 theta, and there's no way to get to that spot. But now you can draw a reference triangle for the cosine of theta. And you can do it from this one, or you can do it from this one. I'm going to go from this place because the unrationalized version is a little bit easier to actually draw our reference triangle for. It tells us that theta is in quadrant 2, so here we are. Our cosine is negative root 3 over 10. So negative root 3 and 10. But again, like you could use 3 root 10 and then 10. You just have to do a little bit more simplification. And then if I solve for this missing side length, I'll get 9 squared, or 3 squared plus y squared equals root 10 squared. Subtract the 9, we should get 1. So that means that our sine of theta is 1 over root 10, which is root 10 over 10. And our tangent theta is 1 over negative 3. Now, obviously, this quadrant we already found is in quadrant 2. So the quadrant of theta is 2. They tell us that information, but we want to find the quadrant of 2 theta, which is different. So again, like theta and 2 theta are not in the same quadrant necessarily. Doesn't mean that they can't be in the same quadrant, but most of the time they're not. So in order to figure out what quadrant 2 theta is in, we have to go back up to our original, which is the cosine of 2 theta being positive. So this is helpful because I know that I'm narrowed down between 2 quadrants now. I'm either in quadrant 1 or quadrant 4. But to come up with the quadrant of 2 theta, we need 2 pieces of data points. We either need to analyze sine of 2 theta or cosine of 2 theta. Sine of 2 theta or tangent of 2 theta, given that the cosine of 2 theta is something that's positive. So I know this for a fact, which means that, again, I'm narrowed down between 1 and 4. But in order to figure out our quadrant, we need another piece of information. And I think that it's easiest to use sine of 2 theta to come up with that information. So my identity is 2 times the sine of theta cosine theta. And I know that my sine theta is root 10 over 10, and I know my cosine theta is negative root 10 over 10, which means at the end I'm going to get something that's negative. So cosine being positive, sine being negative means that I'm in quadrant 4. And again, we already knew this information because they tell us that. This one's a little bit different. We have to evaluate where cosine of, or we know where cosine of 2 theta is, but then we have to evaluate where sine of 2 theta is. And for that we use our identities, and we already found out sine of theta and tangent of theta and cosine of theta, and we can use those values to actually evaluate then where the sine of 2 theta is. This process is not confusing, okay, let me backtrack. This process is complicated, and it can get confusing because we're dealing with 2 thetas and thetas, but once you actually are able to apply what formulas and keep straight in your head whether you're dealing with theta or 2 theta, then this process is a lot less complicated. This is, I think, the place where people mess up the most, is if you're given this type of problem and you're given 2 theta and you have to work backwards. And the key is basically to be able to look at your identities and figure out what you can solve for. Knowing that I have this, which one can I solve for over here given my identities? Given this, what can I solve for? And if you make those substitutions and you can manipulate your formulas, then in general, it just takes some practice to be able to do that. But in general, it goes over pretty well once you get the hang of it.